In this session we are going to be looking at resistance and resistivity and also superconductivity. We know that metals make very good conductors of electricity, and that is due to their structure. So here we can see a piece of resistance wire. If we could look inside the structure of that wire, what we would find is that we had metal ions really surrounded by delocalized electrons. So what we're finding is that in a metal, in each atom of that metal, one or more electrons is so weakly held to the atom that it basically becomes delocalized and it can move from one atom to the next. So we imagine having metal ions, positive metal ions, surrounded by these delocalized electrons. Now then, if we close this switch, then what will happen is the electrons will feel an electromagnetic force as they are attracted towards the positive terminal of this power supply. So as soon as we close this switch here, the electrons immediately begin to experience a force towards the positive terminal, which will be there, and there'll be the negative terminal. And so what will happen, each of these electrons will begin to drift towards the positive terminal here of the power supply. So here these green arrows are indicating a drift here of electrons. We've got the electron drift, which will be from the negative towards the positive terminal of the power supply. And so we get a very gradual drift of the electrons going towards the positive terminal. But of course, as the electrons move that way, they will be involved in collisions. They will collide with metal ions. They will collide with impurities that may be present within the metal. And that will slow them down. And that's why metals have what we call a resistance. And we can define the resistance of a material as being the potential difference across that material divided by the current that passes through it. So in other words, if I need to put a large potential difference across a component to drive even a small current through it, that will mean that that component has a high resistance. Equally, if quite small voltages produce large currents, that means the resistance will be small. As you will recall, current is measured in amperes, which has the symbol capital A. Potential difference is measured in volts, capital V. And resistance is measured in ohms, which has the symbol Greek letter omega. So next we are going to define a property of a material called its resistivity. Now resistance is not a property of a material. We can't say, for example, that the resistance of copper is less than the resistance of iron, because it will depend on the dimensions of those materials. So, you know, if you've got a very short wire made of one metal, like nickel, for example, or iron or aluminium, it might actually have less resistance than a very long copper wire. So dimensions make a big difference, as well as the type of material. What is a property of a material is its resistivity. And so we can define resistivity here. So we define it as follows: the resistance of a 1 meter length of a conductor with uniform cross-sectional area of 1 meter squared. So that's what the resistivity is. If we're talking about the resistivity of copper, what we're talking about is the resistance of a 1 meter length of a conductor, copper in this instance, with uniform cross-sectional area of 1 meter squared. So basically, we're taking the dimensions out of it. In terms of a formula, we can write R equals rho L over A. So R here, standing for the resistance. The Greek letter rho, it's a bit like a sort of a curly P, is standing here for resistivity. L obviously is length and A is cross-sectional area. In terms of units, resistance obviously is in ohms, Greek letter omega. Length is in meters and cross-sectional area is in meters squared, which means resistivity is going to be measured in ohm meters. Now if you think about it, that makes sense, because if we take a wire and we double its length, then the electrons to travel through that wire are going to have to travel through twice as much of the material. They're going to encounter twice as many collisions, one would expect, with metal ions, and so they will experience twice the resistance. So clearly, if we increase the length of a conductor, we will increase its overall resistance. Equally, if we increase the cross-sectional area, we will reduce the resistance of the conductor. And I always think that's a bit like opening extra lanes on a motorway. If you open extra lanes on a motorway, more traffic will be able to pass down that motorway per minute, basically you are reducing the resistance to the path of traffic, and it's the same idea here really, that if you increase the cross-sectional area of a conductor, you will reduce the resistance to the passage of electrical current. And of course the third dependent here, the third thing the resistance depends on, is what material it is. So basically a material with a very low resistivity, like for example copper, is going to be a very good conductor because a certain dimension of that material will have a low resistance. So obviously metals with lower resistivities are going to tend to have lower resistance for a particular length and cross-sectional area. Okay, well we have an example question here. A nichrome wire has length 35 centimeters and diameter 0.28 millimeters. Find the current in this wire when a potential difference of 4.5 volts is placed across the wire. And we're given a big clue here because they tell us that the resistivity of nichrome is 1.1 times 10 to the minus 6 ohm meters. Okay, so basically if we want to find the current in a conductor, we need to know two things. We need to know the potential difference across it, which we do, and we need to know the resistance. Then we can use V equals IR. We haven't got the resistance here, but we have got the resistivity. Now, resistivity is a property of a material. It's important to realise that. Resistivity is a property of a material. Resistance is not a property of the material because resistance will change depending upon the dimensions. It'll depend, as we've already seen, on the length and the cross-sectional area. But we can work out the resistance if we know the resistivity, we know the length, and we know the cross-sectional area. Because, remember, resistance is always equal to resistivity times length over cross-sectional area. Resistivity has got the symbol here rho. Greek letter rho stands for resistivity, okay, measured in ohm meters. So here we've got the resistivity is 1.1 times 10 to the minus 6 ohm meters. We need to multiply that by the length of the wire. Now we need to be consistent in our use of units. We've got the resistivity here in ohm meters, so we need the length in meters, 0.35 meters then. Now, cross-sectional area. Well, if you think about a wire, basically with a wire, what you're going to have is essentially a circular cross-section. We know the diameter of that cross-section is 0.28 millimeters, and of course the radius is half the diameter, and the area of a circle is pi r squared. So on the bottom here we're going to have pi multiplied by the radius, which is half the diameter, so half of 0.28 will be 0.14, and again we want that in meters, so milli, prefix milli times 10 to the minus 3. Don't forget on the bottom the radius has to be squared, and there we go. We've got resistivity, we've got multiplied by length. The area here is going to have units meters squared. Obviously the meters times meters, meters squared on the top and bottom will cancel. The unit will come out in ohms for resistance at the end. So let's work down here. And we'll come out with an answer of 6.253 ohms, which really, because the data in the question was given to two significant figures, we really ought to round that here to 6.3 ohms. Now of course when we've done that, working out then the current is trivial because we know that V equals I times R. Yeah, R is V over I, V equals I times R. So I, current, will equal the potential difference divided by the resistance. Well, we've got 4.5 volts across this wire. Its resistance is 6.3 ohms. Probably I would put that in as 6.253 just to avoid a rounding error. When you work that out, you will get 0.72 amps. That's basically all there is to it. Okay, well, we've had a look at resistivity, and what we've seen is that different materials have got different resistivities. That's different resistances for 1 meter lengths with uniform cross-sectional area 1 meter squared. We've seen that a metal like copper is a particularly good conductor because it has a very low resistivity. It's good at carrying electricity. A wire made out of copper will have a lower resistance than most of the metals, and therefore we will have less energy losses in that wire when we transfer electrical currents through it. But even for copper, the resistance certainly isn't zero. It is still significant, and we will still get electrical energy losses in wiring made of copper. What we do see is that the resistivity of any material will tend to decrease with temperature. So If you look up the resistivity of a particular material in a data book, generally the resistivity will be quoted at a particular temperature. As the temperature is reduced, the resistivity will tend to drop. Equally, if you increase the temperature, the metal ions start to vibrate faster in that solid. That will tend to increase the resistance of that material, and hence its resistivity. There are, however, some materials for which, as you cool them down, when you reach a certain temperature, the resistance, the resistivity of that material will suddenly drop to zero. So whereas for what we call non-superconductors, so for what we call a non-superconductor, normal materials, as you cool them down, yes, the resistivity of that material will decrease, but even at the absolute coldest temperature we can get, which corresponds to minus 273 degrees Celsius, what we sometimes call 0 Kelvin. Kelvin is an absolute temperature scale because it starts at 0. The coldest temperature you can get is 0 Kelvin, which corresponds to minus 273 degrees Celsius. Even when you cool it down to that temperature, so basically at that temperature, you know, the ions of the metal won't even, the atoms won't even vibrate at all. If it's a solid, it'll just be stationary. Really, at that point, even then, there is still some resistivity of the substance. But for a superconductor, as you cool them down, yes, the resistivity will decrease as it does for non-superconductors. But for a superconductor, when you cool it down to a certain temperature, the resistivity will then suddenly drop to zero. So we can define a superconductor as a material that will have zero resistivity below a certain critical temperature. Now there are certain elements that do become superconducting, but only at extremely low temperatures. I think even something like aluminium may become superconducting, but only when you get it down to about minus 272 degrees Celsius. So you have to be down at almost absolute zero. There are some alloys, some metal alloys, typically of transition metals, together with certain other elements, that actually form superconductors that become superconducting at a much higher critical temperature. But we're still often talking about temperatures that are, you know, 70, 60, 70 Kelvin maybe, so you're still getting down to, you know, perhaps minus 200 degrees Celsius. So still talking about very, very, very cold temperatures. But a superconductor is nevertheless a material that will have zero resistivity below a certain critical temperature. That is the definition. A lot of research is going on to try and discover new superconductors that can operate at higher temperatures, because obviously the property is potentially extremely useful. If we could actually have a conductor with zero resistance, what that would mean is we could actually transmit electrical power with zero energy losses. So at the moment, as you transfer electricity through power cables, the resistance of those power cables, as you pass a current through that resistance, you are going to get significant energy losses. The cable is going to get hot. If it had zero resistance, the cable wouldn't heat up. You would have no energy losses at all. And so that would be an incredibly useful property. But obviously at the moment, the amount of energy you use cooling the current superconductors down to these incredibly cold temperatures would negate the advantages. Also, if you could have a superconductor, you could produce extremely powerful magnetic fields. You're producing things like electromagnets. At the moment, when you put a current through the wiring of the electromagnet, you're going to get a lot of energy losses. You could have superconducting wires, superconducting cables. You can, again, reduce those energy losses essentially to nothing. So a really, really useful property. But there we have it then. What do we need to know about superconductors? Well, we need to know simply that a superconductor is a material that's going to have zero resistivity below a certain critical temperature. I think we need to have an understanding that for most superconductors, that's going to involve cooling the material down to extremely cold temperatures. Well, all superconductors really at the moment got to be cooled down to extremely cold temperatures. What are the uses of superconductors? Well, clearly to reduce energy losses when we transmit electrical power, and also producing strong magnetic fields. Again, superconductors can be used for that application.